Welcome back, everyone. Today, we're jumping right into our explainer on the transport layer. Now, in our previous discussions, we've talked a whole lot about how data travels across the globe, right? But today, we're zooming right into your very own machine. I'm super excited to guide you through this because we're going to unpack the invisible transport system that takes the incredibly chaotic, massive rush of internet traffic arriving at your computer and perfectly sorts it all out. We are talking about TCP, UDP, and the magical numbers known as ports. All right, let's dive in.
So here's our roadmap for today. We'll start by looking beyond the IP address, then we'll cover ports, TCP, the famous three-way handshake, UDP, and wrap it all up with choosing the right transport.
Starting off with Section 1, Beyond the IP Address.
Think about this fundamental problem for a second. Your computer's IP address acts exactly like your building's street address. The network layer does a phenomenal job of getting millions of packets from halfway across the world right to your front door. But once those packets cross the threshold of your machine, well, how do they get sorted? How does a packet actually know if it belongs to your web browser, your email client, or that super intense multiplayer game you've got running in the background? You see, the IP address alone simply cannot solve this routing mystery.
Which brings us to Section 2, Ports, the application extensions.
Imagine your computer as a large corporate office with just one single main telephone number. That number is your IP address. If someone calls it, they just reach the front desk. To actually speak to a specific person or a specific department, you need an extension number. Well, in networking, these extensions are called ports. Instead of all your data bottlenecking into a single confusing funnel, port numbers neatly separate the traffic. They route specific packets to specific applications that are literally listening on those exact port extensions. To make this a bit more concrete, let's look at what we call well-known ports. These are the numbers ranging from 0 to 1023 that run quietly in the background of your daily digital life. When you browse the web, your browser is automatically reaching out to port 80 for HTTP. If you're securely logging into a remote server, you're using port 22 for SSH. Need to resolve a website name? That happens over DNS on port 53. Transferring files? That's FTP on port 21. Because these numbers are standardized, client applications always know exactly which extension to dial to get the right service. It's totally seamless.
But hey, we aren't just limited to those well-known numbers. Actually, there are up to 65,535 total ports available on your machine. While the first 1,000 or so are reserved for those standard system services, the rest are registered or completely dynamic. So the really crucial takeaway here is that when you're running complex activities like peer-to-peer file sharing via BitTorrent, or even just having dozens of browser tabs open at once, your computer is dynamically assigning these higher port numbers to keep every single conversation perfectly isolated and organized.
All right, moving on to Section 3, TCP, the Reliable Courier.
TCP stands for Transmission Control Protocol. Now, think of TCP as a meticulous delivery driver who absolutely refuses to leave a package without getting a signature. It's what we call a connection-oriented and stateful protocol. In plain English, it means it provides an end-to-end error-free bit stream. If a packet gets lost out there in the chaotic internet, TCP notices and retransmits it. If packets arrive completely out of order, TCP sequences them back together perfectly. This meticulous reliability is exactly what you need when you're downloading a file or loading a web page. I mean, even a single missing byte could corrupt the whole thing, right?
And that leads us directly into Section 4, the three-way handshake. So TCP's flawless reliability doesn't just happen by magic. It actually requires a highly formal introduction before a single byte of actual application data is ever sent. And it's a lot like a formal business introduction. This concept was originally introduced by Ray Tomlinson way back in 1975 to prevent old, delayed packets from confusing the system. Here's how it goes. First, the client sends a SYN packet. It's basically saying, hey, I'd like to sync up and start talking, and here's my starting sequence number. Then the server replies with a SYN-ACK, meaning I acknowledge your request, I'm ready to go, and here is my starting number. Finally, the client replies with an ACK saying, I acknowledge your number, let's begin. It's only after this incredibly polite three-step dance that the real data actually starts flowing. So just to summarize TCP's rich feature set, it establishes a firm connection, it guarantees reliable delivery by acknowledging absolutely everything and retransmitting whatever is lost, it uses sequence numbers to preserve the order, and it even uses flow and congestion control so it doesn't overwhelm the receiver or the network. But and here is the catch. All of this incredible overhead, the handshakes, the acknowledgements, the constant state tracking, it means TCP can be a little bit slower.
Which brings us to Section 5, UDP, fast but unreliable.
That meticulous overhead we just talked about is exactly why TCP has a wild counterpart, UDP, which stands for User Datagram Protocol. If TCP is the careful driver demanding signatures, UDP is the delivery driver who simply chucks your package over the fence as they speed past your house. It is a connectionless and stateless protocol. There is absolutely no polite three-way handshake happening here. It doesn't check if the server is ready, it definitely doesn't guarantee the data arrives in order, and it absolutely does not retransmit lost packets. It just encapsulates the data and fires it off in a rapid-fire, best-effort delivery.
Now you might be sitting there wondering, why on earth would we want a protocol that loses data? Well, for real-time applications, speed is everything. Literally everything. Think about internet telephony, like Skype, streaming live video, or fast-paced online gaming. If you're in a live video call and a frame gets dropped, you really don't want the protocol to pause your entire call just to go back and fetch that missing frame 2 seconds later. That would completely ruin the real-time experience. You would much rather just accept a tiny visual glitch on screen and keep the video moving forward. So for these applications, a dropped frame is vastly preferred over a delayed, retransmitted one.
And finally, Section 6, choosing the right transport.
When we put these two wildly different philosophies head-to-head, it all really comes together. TCP gives you that connection-oriented reliability. It's going to retransmit any lost data to ensure flawless accuracy, which, as we know, is non-negotiable for loading web pages, downloading files, or sending emails. UDP, on the other hand, gives you connectionless speed. It readily accepts data loss to maintain real-time pacing, making it absolutely critical for streaming media and VoIP. The true beauty of the transport layer is that it perfectly accommodates both of these needs. Together with those 65,000 different port numbers we talked about, TCP and UDP seamlessly sort the vast chaos of the internet into the beautifully organized functional applications right on your screen.
Which leaves me with one final question for you to ponder. As you sit there streaming this explainer right now, taking in this information and listening to my voice, which invisible protocol and which specific port do you think is working tirelessly in the background right this very second to bring this exact content to your screen? Keep that in mind the next time you open a browser tab. Thank you so much for joining me for this explainer, and as always, stay curious.